So, hello everyone, let's solve MEXT Physics Exam 2014, okay? It's question 2. It's the question that he gives you a line and then you have a ball over here. The ball is going to fall, the length of this line is A, the mass of the ball is M, the line is going to fall. This is the point B, it is in the distance A over here. So that when the ball falls, it will touch over here, okay? So it will do something like this. There is like something here to stop the ball when it hits. So there is like a pin over here, or like this pencil over here, okay? Like there's something over here. So the ball is going to hit, and then it will start making a circular motion over here, okay? It will start making a circular motion like this. So first of all, this example is very interesting because first it was an example given in Galileo's book, okay? So I'm going to show you first of all, because my point with this with solving this question is more of analyzing it and talking about it than just giving you the answer, okay? I think it's more important. So this is the book that I'm showing you. This is its name. It's written in Portuguese, so this is the name of the writer, okay? So page 143 if you need, but you don't need the book for now. So look, this is the example in Galileo's book. He was saying that if you let the ball fall from here, it will always hit back. It doesn't matter if you put any knives over here. This ball will always go to the same other level, unless you put it very down, so that you don't have enough line so that the ball can do the whole loop. What do I mean by this? Like, one second, let me find the other page over here, because it's very interesting. Like, look how he explains it. Look, so you see, he's telling you that it doesn't matter, as long as we're going from point C, by the conservation of energy, we need to go back to this line, right? But if you put the pin very low, you won't have enough lines so that it goes upwards. So, but we will still have energy. So what is going to happen? What is going to happen is that you will end up having this line looping in your pin, right? Because you still have energy, but you don't have enough line to go to the level where you were. So it will end up looping in your pin, okay? So he gave you some situations over here that in the question he told you that B is bigger than A divided by 2, remembering that A is all of it, B is this part over here, and it's smaller than A. Well, it's smaller than A. Why? Because if it was bigger than A, then the pin would be it would be out of our range, and our motion will just go up there, go down, right? But why is he telling you this, that B must be it must be bigger than A divided by 2? Now, this comes from Galileo's, like we are not using this immediately in the question, but it's important to tell you this. Why? Now in Galileo's, when you are solving it, we are using more the radius over here. You see, we are going to talk about the radius when he explains it. So what do I mean by this? Look, imagine like this. Imagine that you had this ball over here, okay, with some angle over here, and this is the potential energy, okay? So when it's going to fall, it's going to hit a pin maybe over here, something, and then it's going to make a circular motion, okay? So what I'm going to call is that now instead of using like here B, because B, remember what was B? This. The question of the max just make it a bit strange. So let's talk first about R, because now I'm just talking about the idea and then I'm going to solve the question. Okay, so I'm going to call this D and the whole thing over here is Z. Okay, Z, okay, the height. So my drawing is not very good, but I'm trying to draw this. Okay, I'm trying to draw you this. Okay, so the ball is in Z and then it's going to fall and then it's going to make a circular motion with a radius of R. Okay, so notice something, that the energy, like over here I did it wrong, right? So it would be like something like this, and then the ball would fall something like this, and then we are going to have the point P over here and make a circular motion right here, right? So this would be our D, this would be our Z, right? So what is our energy over here? Okay, now like the ball is falling and it hits the pin, the pin's over here, it hits it and start a circular motion. Okay, so look, I'm going to consider this line over here where the potential energy is 0. Okay, so notice, what is the first energy that we have? We only have potential energy, which is mg multiplied by the height with z, right? And then we will have potential energy over here and kinetic energy, right? So what are we going to have? Potential energy mg, but the radius is d, so the diameter is 2d, plus the kinetic energy. So over here, when the ball is falling, it will hit the pin over here and it will start making a circular motion, right? So here we have velocity, right? So mv squared divided by 2. Okay, so why am I doing this? So look, the mass, we can put it out and then we multiply everything by 2, so we will have that v squared is equal to 2gz minus 4gd, right? Okay, so v squared is equal to, let me take the 2g out. Okay, so 2g out, so we'll have z minus 2d, right? Now notice something, you have over here v squared, so v squared is always a positive number. It doesn't matter because it's squared, so it's always positive. So if it is equal to something, so this equality, this number over here must be a positive number too, right? Because if this is a positive, then this must be positive. So 2g and what can make this part over here negative? Because 2g is constant, 2 is a number, g is 9.8 something, so it's positive. So what we need to make sure is that our z minus 2d must be bigger than 0, right? Bigger or equal to 0. It can equal to 0 also, because if v was 0 squared, it can be equal to 0, right? But the point is that this part over here, it can't be negative, so we will have that d must be smaller or equal to z divided by 2. And now we have a relation over here which tells us that our diameter, our radius of this circular motion coming here must be half of the height, that half or smaller than the height that is happening. So remember from the experiment that I just told you that Galileo wrote in his book, that if d was not smaller than this, then you will have the ball just going over here. It would hit the pin over here, but you will have enough length, you will have enough line so that it will just go over there bounce back, and so it would do it will conserve the energy easily. It wouldn't need to make a loop over here, okay? It only makes loops when your diameter is equal or smaller than half of your height. And this is why he gave you this information over here, okay? Now he told you here that it is bigger, but you need to notice that here he's talking about B. He's not talking about R, okay? So this would be our R, or in the case I use a D, it can be our radius, okay? Now notice that R plus B is equal to A, okay? So this is why he told you that it must be bigger than A divided by 2, because R must be smaller or equal to Z divided by 2. Now I know I took too long and I didn't even start solving, but I think that the information is the most important, and this is going to be a very long video, but I think that what we need to do is to take the information that we can from the previous exams so that we can do well in this exam. Alright, so let's start solving it, and then I'm going to solve an extra question, okay? Let me just try to take out this shadow over here by pushing the camera a bit. Yeah, I'm done. It's the shadow of my own cell phone. This is sad. Well, I can't do nothing about that. So let's start solving. Now here I have the questions, okay? So now let's start solving it, okay? So the first question, he's asking you the speed of the ball in point B, the tension in point B, and then he's asking you the tension in the line, right, at point D when it starts the circular motion, the relation of A and B so that the line does not bend, and case of B. Now in 5, when case of B is equal to A divided by 2, at what speed does it bend? And he's telling you that it will bend, okay? So if you want to try to solve it now by yourself, just consider this line to be the potential energy of 0. Remember that here you'll have a potential energy of mg multiplied by A, because all this is A, and then find the kinetic energy over here, okay? So try to solve it. Now I'm going to start solving it, okay? So look, what did we have over there was potential energy, right? Let me take the pencil over here. mGA, right? Potential energy. This, now the energy over here when the ball falls, this what I consider it to be 0 potential energy, so all I'm going to have is kinetic energy, so velocity in B squared divided by 2. So I already found my answer. The velocity in B is equal to, the m's will cut out and the 2 will go multiplying, so 2GA in the square root. So this is our first answer. It is G, okay, in your paper. Now this was the easy part, right? Easy thing. We only applied the conservation of energy, so we are very used to it. So the tension in point B. So what do we have happening here in point B? What is happening in point B? So over here in point B, imagine this is point B, okay? So when the ball falls in point B, what is going to happen to it? Well, we have over here T, tension, right? And we'll have over here its weight, right? Its weight, that I'm going to say it's P, okay? Let me try to zoom a bit. Okay. So now notice that T is bigger than P, because it doesn't. Now you might think, well, I have tension over here and weight over here, but it's not falling. But remember, you have now circular motion, okay? So you have a centripetal force that's acting. So T the tension minus your weight, which is mg, must be equal to ma, right? Newton's second law. But this acceleration over here, this a over here, it's the centripetal acceleration, which is equal to the velocity squared divided by the radius, okay? Some radius over here, I'm going to call it x, a radius of your circular motion. Okay, now what velocity is this? Well, it's the velocity in this point. It's the velocity b. Now, this is the thing. Now, what radius are you choosing? Now, you can't choose this radius over here because now you're not doing this circular motion yet. You are doing this one over here, the big one, okay? This whole circular motion. It happens that here it's going to hit something and then you will start another circular motion. But until then, your radius is a, okay? So this x over here is going to be a. So our centripetal acceleration is going to be vb squared divided by our a, okay? So t minus mg is equal to, well, the mass multiplied by a, but a is vb squared divided by a. What is vb squared? Well, vb is this squared, then it is 2ga divided by what? By a. So we are going to have that the tension is equal to 3mg, okay? So this is our answer. The a's over here will cut out and then you will sum it and you'll have the answer over here, which is C in the answer book, okay? So notice two things about this, that we knew the velocity that we needed to use we needed to find it in the previous question, and you can't mistake it with this r over here. Now we are going to talk about this circular motion. Until now we are just analyzing this movement over here as if this spin never happened. Now we are going to put this spin over here and it will hit and start doing the circular motion, okay? So the next question is the tension on D. Now look, this is going to happen. The ball is hitting over here and then it's going to the point D. So what do we have in point D over here, okay? This is our point D, okay? What forces do we have acting over here? So we will have the tension over here, right? The tension of the string, because it will loop over here, but the string is pulling here. It's not a stick. He can't pull you off. He's always pulling in, okay? And the other force that is downwards too, it's your weight, right? mg. So both the forces are acting downwards. So notice over here, the T plus the weight now must be equal to something, to ma, right? But remember, now again we are having the centripetal acceleration, okay? So this is the centripetal acceleration, okay, in point D. So now we are going to use the velocity in D, okay, squared, and x now represent another thing, right? We need to find x, the radius of our circular motion. It's now no longer a. Our radius is this r over here. And notice in the question that I even put it over here, r plus b is equal to a. So r, let me do it in blue, r is equal to a minus b, right? If this is all a, this is b, then a minus b is r, okay? So this is going to be our r, and our x is our r, okay? Because now we are doing the second circular motion. But notice that we don't know our velocity in D yet. So we need to find our velocity in D. Just remember, this tension over here, it's what we are looking, the tension on D. So the tension on D is equal to m, the velocity in D squared, divided by x. But x is our radius, which is a minus b. Now this is minus mg. Now I'm going to put this one on hold and I'm going to find the velocity in D, even though he didn't ask us, so that we can complete our question, okay? So that we can find what he told us. So how can we find our velocity in D? If you want, try to think about it for a second, or pause the video and try to solve it. Now notice, so I'm going to use the conservation of energy again, and I'm not going to bother from the beginning. I'm going to start over here. Here I know the energy that we have over here. We have the kinetic energy in point B, and our potential energy is 0. So I'm going to find what energy does he have here. How am I going to do this? Well, over here, look. In point P, what is our energy? Over here. In point P, what is our energy? It is mVb squared divided by 2, right? We only have kinetic energy. Now, in point D, so the energy conservation of energy. In point D, what energy are we going to have? We are going to have kinetic energy mVd squared divided by 2 plus a potential energy, because now we are no longer in this 0, we are over here. But how much is this? Well, if this is the radius and this is in the top of it, then this is 2 times the radius, right? So it is going to be mg multiplied by the height. The height is h, but h in our case is 2 times the radius. 2 times the radius, okay? If anyone didn't understand it, the ball is going to loop. This is d, and this is the top of the circle motion, so this is 2 times the radius. So 2 times, but what was our radius? It is a minus b. So a minus b, okay? So now I know everything. I just need to find the velocity in d. Okay, so let's find our velocity in d. Now vb is over here. We are almost already memorizing it. So m multiplied by vb squared to ja, and I'm going to multiply everything by 2 so that I can get rid of these 2 dividing over here, and I can cut the masses, right? So I don't need to keep carrying the masses. So vd squared plus, remember I'm multiplying everything by 2, so I'll have 2 multiplied by 2, so it is 4g, because I cut the masses, a minus b, okay? So the velocity in d squared is equal to 2ja minus 4ja plus 4jb, okay? If you have any problem with what I'm saying right now, you just take a paper and do it by yourself, okay? These parts where there is not much physics, you do it by yourself. So 4gb minus 2ga, right? So this is our velocity, our vd squared. So I'm going to put this information now over here, okay, to find the tension in D, okay? So TD is equal to m, I'm just taking it over here, so vd squared, it is 4gb minus 2ga divided by a minus b minus 2mg, okay? So our TD, well, notice that I have g over here and g over here. It can go out, and then I'm going to take out the mg, okay? So it is equal to mg. Now here I have 4b minus 2a divided by a minus b minus 1, okay? If you put the mg back here multiplying, you'll get this back, okay? So this is the part of algebra. We are more focused on physics now. So taking the minimum multiple, I don't know if it's really called like this. So mg 4b minus 2a minus a plus b divided by a minus b. I just did it a bit faster than usual. So we are going to have over here that the tension in D is equal to mg. Now notice, for B plus B it is 5B minus 3A divided by A minus B, and this is our answer. Okay, this is our answer. It is F in your notes. So I took notes of the things because the paper was full over here, so I took notes of the most important thing that we did. If anything was unclear, just go back in the video. So now let's go to question 4. Okay, the relation of A and B so that the line does not bend. Okay, so how do we approach this question? So what does he mean when he's telling us this relation so that the line does not bend? So notice, what energy do we have over here? The energy in point B, kinetic energy. What energy do we have here? The same thing that we just did, but now we are going to take the velocity in D a bit different, because now look over here, where did we did it? We did it over here when we are calculating the velocity in D. What was our assumption? Was that, look, when we were talking about the height where D is, we were talking about B and A, right? So this is what we are going to change now in our approach for the next question, because it's the same thing, but the approach that we need to do is different. How's that? Look, the energy that you have in point B is what? In point B, it's mVb squared divided by 2, right? Now you will have later mVd squared divided by 2 plus mg. Now I'm going to just call it h. Now what's the thing that we need to notice is that the relation that we need to make so that the line doesn't bend is that he needs to make this top thing, he needs to make it to the top. What do I mean by this is that and this is it's like in the cinematic, when you're studying cinematic, you know that when you have that loop over here and then you have a bicycle and the bicycle is going there, and then he's asking you in what velocity does this needs to come over here so that it can make the loop. So how can you solve this problem? Well, it's by finding a new type of the velocity in D. How is that? Is that when he's making the loop, the minimum, so that we are going to see the relationship of them in the minimum way so that we can make this loop happen. And what's happening when this loop can happen is that the tension is 0. We neglect the tension because it's the minimum condition. So the only thing that is acting in point D over here, it's your weight. So now it's mg that is doing the centripetal force, which is md squared divided by the radius. Okay, so this is our condition, is that now our vd squared, our velocity in D, is equal to what? The mass will cut out, so it's rg, right? So this is our velocity in D. But what was our r over here? Our r is a minus b. So our velocity in D. Now notice that this is the minimum velocity, okay? So our velocity in D must be equal to squared is equal to a minus b g, okay? G over here. So let this over here, note it over here. We are going to use it. How are we going to use it? Over here, our energy, if we say that we have this energy over here, m, now D squared is what? It's a minus b g divided by 2 plus mgh. Now h is what? H is our height, so it is it is 2 times the radius, right? 2 times the radius. I'm just going to say 2 times r, right? Okay, r we already know, it's a minus b. This is not my point. My point is this is the minimum energy that we need to give it so that we can make the loop, right? Because we took the minimum velocity. So the energy that we need to have in point B must be bigger or equal to this. If it was any smaller than this, then we would have this energy smaller, but we can't have any energy smaller than this because we want the energy, the sufficient energy, so that we can, so that the line doesn't bend. So we need it to be bigger or equal to this. Our what? Our mvb squared divided by 2. Okay, when we are taking the velocity in d as the minimum velocity to complete this loop. Okay, so the m's can cut off now, and VB squared is 2GA. I'm going to multiply everything by 2, so I'm going to have GA minus B plus 2 times 2 is 4, R is A minus B, and we have a G over here. We can cut the G off too, right? So we have that 2A is bigger or equal than, there's no G anymore, A minus B plus 4A minus 4b. Okay, so let's put all the a's over here and the b's over there. So we have minus b minus 4b, it's minus 5b, goes to the other side, so minus 5 plus 5b, right? Because it goes to the other side, plus 5b, bigger or equal. 4a plus a, it's 5a, minus 2, 3a. So we will have that a is smaller or equal to 5 divided by 3b. Okay, so this is our answer for the fourth question. This would be D. Okay, so remember, he wanted the condition so that the line does not bend. And how did we approach that? By remembering this other example of different types of question, so that we thought, well, the minimum velocity d, so that it doesn't fall, is when the tension is you neglect the tension because it's almost falling but not falling. We found the mg with this velocity over here, and then we found the minimum velocity d, and we said that the energy we need to give in point B must be bigger than this energy, because more than this, well, we can complete no problem. Okay, so now let's go to problem number 5, and he's asking you, in case B equals to A divided by 2, what speed does it bend? So he's basically telling you this. Now we have that the pin is in the middle over here. Okay, so we have half the radius is A divided by 2, and the other one is A divided by 2. Okay, so how can we approach this type of question? And now, so it doesn't seem that I'm just like, I found the answer out of my head. I want to solve another type of question with you. So if you already know how to solve this, try to solve it by yourself. But I'm going to try to solve another type of question, and then we go back to this one. Okay, so, and this question already fell, it happened in Max, in I think College of Technology exams, maybe in 2010, 11, something like this. But I have it in a book over here. It's a Portuguese book also, so this is the name of the book if you want. So this is the question that I'm going to solve over here. Okay, so you have this block over here, and there is this small block, and he's asking you at which height h, like over here, this is h, when the block is over here, that the block falls and stop having contact with this block over here. Okay, so why am I solving this? Because this is the same type as notice that it is the same type of question that we have. The only thing is that our example is a ball coming over here. Okay, so how are we going to solve this over here? So I have over here our block. This is R. I don't think we need its mass. Yes, we don't need its mass. We have gravity over here. Okay, so we have gravity over here. So how can we approach this type of question? Well, it's that you will see that the ideas, like it seems when first like the person chose this idea, it might seem like, how did he figure this out? This is the block when he's going to fall. Okay, so the thing that I'm trying to tell you is that the idea why I'm going to solve the question like this is because I seen this question before. Okay, so this is the question, the block, the position when it's going to fall. I'm going to suppose it's over here. Okay, so I'm just doing a lot of lines over here. This is a tangent line over here. Okay, so, and I'm going to call this angle over here, I'm going to call it theta. Okay, and this is really weird, right? Because he never told anything about an angle, but I'm already assuming an angle. Okay, so why am I going to assume this angle? Because I can use this angle over here, right? Because if this is theta, then this also is theta. Okay, okay, so the point is, now let's draw the diagrams of the forces that are acting in this block over here. Okay, this block over here, what forces do we have acting on it? This is its center of mass. Okay, so notice that we have over here, I'm going to put our axis. Okay, our axis, this is our radial axis, okay, passes to the center. Notice that this angle over here is theta, which is this one over here. Okay, so what forces do we have acting? Well, the first force that we have acting, since we have gravity, we have its weight, right? Its weight over here, it's acting. We have P over here, its weight. What other forces do we have? Now you might think, well, we have the contact force over here, the normal force, but this is where you need to do something, because the condition that he told you is that when the block is almost falling. So in this condition, we no longer are going to consider that when the block is making contact. It's just as the question of the loop in the top of it. Okay, very similar. So the only force we are going to consider is its P. Okay, so next thing that we are going to do. Okay, so notice that this block over here falling is making a it's like making a circular motion with a centripetal force over here. Where is the direction of the centripetal force? Well, in the centripetal direction, right? This direction over here. So I'm going to compound this vector over here in this direction over here. Okay, notice, like I'm going to see what P, because I want to say that I have a force, which is this force that's acting over here in this part over here, is equal to what? To my centripetal acceleration, to m, to the mass of the block multiplied by the centripetal acceleration. Okay, but what force acting over here? Now this is a right triangle. If you remember the sine and cosine laws, this side over here, it is P cosine theta, right? I think this is no problem. Okay, P cosine theta, and this part over here is P sine theta, but we are not going to care about it now. So P is what? If you have any problem with this, just imagine this is your P, this is theta, and we want what? This is x, right? So the cosine of the angle is equal to what? To the edges divided by the hypotenuse. So x is equal to P cosine theta. Okay, so this is what I did over here. Okay, no problem. So P is equal to what? Mg cosine of the angle equals to ma. Now this acceleration is what? it's the velocity at this point over here squared divided by your radius, right? Which he gave you, r. Okay, so m is going out. So now we have an expression for our velocity, and I'm doing many things that you might think he's not asking us, right? Like the angle, the velocity, but it will all, it's all part of the plan. Now notice that here we have an expression for the velocity that we found by the force, by the condition that he gave us, that the force is losing contact. Now we are going to use the energy, because notice you can do this by two ways. You can consider by many ways. You can consider the potential energy wherever you want. I'm going to consider the potential energy here as 0. Okay, here our potential energy is 0. Our initial potential energy. So in this point we had potential energy, right? Let me just save this one. This is 1. Okay, so now let's find another one. Now we are going to use energy to find the other equation. How do we do this? Well, the first thing was he had a potential energy mg. Let me use the blue. H is r, right? So it is r over here. So r. Now this must be equal to the energy in this point over here, right? So in this point he has mv squared. Now notice that this velocity is the same as this one, and this is the thing that we are looking for, divided by 2, that's kinetic energy, and he has a potential energy plus mg multiplied by some height. What height is this over here? Because this is its height, right? Now notice that this is r, so this part over here, it is r cosine of the angle, right? This side over here, this is our height, and this is r cosine of the angle. Same thing as we did over here with the force P. Okay, so this is r cosine of the angle. Okay, now notice that we have this expression with v and cosine of the angle, and we have this expression with this expression with v and cosine of the angle. So we can find the cosine of the angle, and remember, what are we looking for? It's our h. Okay, our h is this one over here. So our h is r cosine of the angle. So if we find the cosine of the angle, we can find our h that he wants. So let's solve this. So mgr, we can cut off the m's, right? So let's start again over here, and let's multiply it all by 2. So 2gr, and let me send this part over here. So 2gr cosine of the angle must be equal to, I cut the m over here and I multiplied everything by 2, so only v squared. Okay, so we are having that v squared is equal to gr 2 minus cosine of here we have 2 multiplying over here 2, right? So there is a 2 over here because 2, and then we have 2 over here also. So I forgot to multiply over here by 2. Okay, so there is 2 over here. 2 cosine of the angle. Okay, but remember, v squared is equal to this. So in place of v squared, I'm going to put rg cosine of the angle is equal to rg 2 minus 2 cosine of the angle. So I'm going to cut rg, so I'm going to have that minus 2 cosine of the angle plus cosine of the angle is 3 cosine of the angle is equal to 2. And now we have a very interesting result, because cosine of the angle is equal to 2 divided by 3. And this is you will notice that I think in the other example it will give us something very similar, because this doesn't depend on anything. It doesn't depend on the radius of our ball over here. It's telling us that where it's going to start falling, it's making an angle of 2 divided by 3. Okay, and this is very, very, very interesting. Okay, like this angle, you can use this example, like many people, even like of competitive exams, they even memorize it. Okay, but you need to understand very well what angle you are talking. You can't say that this is your angle. Okay, this was our angle. 2 divided by 3. Okay, it's cosine. So our h is r multiplied by cosine. So our h is equal to 2 divided by 3 r. So this was the height from where it will start falling. It will stop having contact over here. So why did we do all this? Number one, because it's a very interesting example and it can help you with the questions. And there is a question of the max that already had this. So now let's solve the last item. So now look, I didn't even bother to draw the whole circle because he told us that what's going to happen is that it's going to fall. So when b is equal to a divided by 2, it's going to something over here and it's going to fall, and he wants to know the speed. Okay, what is the speed? So this happens. Now notice that we are going to make the same things over here. Okay, so if you want to try to solve it by yourself, now notice that as b equals a divided by 2, our radius, remember our sheet, like these were some things that we found, right? So our radius, now if b is equal to a divided by 2, then our radius is equal to a divided by 2, right? A minus a divided by 2 is a divided by 2. Okay, so just to make it obvious over here. So look, I'm going to, let's say that it's going to fall over here. Okay, over here our ball is going to lose contact and it's going to fall. So this is, again, now really pause this video and try to, like, what forces are acting over here? Okay, what forces do we have over here that we have acting? Okay, so let me just put over here. So this point over here was B, and this point over here was D. Okay, you can see it clear. Okay, D. So I'm going to call again this angle over here theta. Okay, I hope you are trying to solve it. You can put over here something like this. Okay, notice that I'm going to do the same thing. The only thing now is what condition does the force needs to obey so that we have the what he wants from us. Yeah, I lost my words now, sorry. So look, if this angle over here is theta, then this angle over here also is, right? This angle over here is theta too, right? I don't remember the name of this theorem, but at this point over here, in this point P, what forces do we have acting? Do we have tension in the line? Well, this is the thing, again, we don't. Why? Let me just do the lines again over here. We have over here P, right? P over here. We can have over here, and we have the radial that points to the center line over here. Okay, we can put a line over here too, just to make it look good. Remember, this angle over here is theta. Okay, we don't, why are we not going to use the T, the tension? Because we are considering that in this point it is bending. Okay, at what speed it bends. So if it's bending, then the tension is not applied anymore. So again over here, so this part over here, the part of the component of the weight, of the force of the weight that is applied in the centripetal direction is P cosine of the angle, that must be equal to m, the velocity that he wants at this point. He wants this velocity over here, m v squared divided by our radius. Our radius now is what? Remember, it is A divided by 2, okay? Our radius. This is our R, okay? Our R of the circular motion, so it is A divided by 2, okay? Remember, this is our centripetal acceleration of the circular motion, okay? So again, we are going to have what? That mg cosine of our angle is equal to, now 2, because A divided by 2, right? 2m v squared divided by A, okay? So we are having that v squared is equal to ag cosine of this angle divided by 2, okay? So how can we use this now? Now we found, as we did earlier, we found an expression for the velocity, but remember, we don't know this cosine over here. How can we find it? Well, now we use the force. Now we are going to use the energy, okay? How do we do this? Let me remember, what energy did he had in point B? In point B, he had only the kinetic energy. Its mass, velocity in B squared divided by 2, and then he's going to have this velocity over here, mv squared, which is the same as the velocity that we want, divided by 2. Remember, it's 2 now because it's the kinetic energy. We're not talking about the centripetal acceleration, okay? Plus, so notice, so what energy does he have over here? Well, he had the kinetic energy and plus the mg h. But what is its h over here? What is the value of h? Let's find it out. So h over here we have r, and over here we have what? Remember, this part over here, this part is r. You can see in this triangle over here, if you draw it over here, this is r, so you can find this easily. This is r cosine of this angle. So this is your h. This is h. Your h is equal to r1 plus cosine of your angle. Okay? This is your h. A bit of geometry, okay? So I'm going to cut off the m's multiplied by 2, so vb squared is equal to v squared plus 2, because I'm multiplying by 2 everything, g multiplied by h, but our h is r 1 plus cosine of our angle, okay? Our vb was what? Vb squared is 2ga, so 2ga equals v squared plus 2gr 1 plus cosine of our angle. Now you could have done it differently over here. You could have put in the cosine alone so that you find the v, but I want to show you the result of our cosine again because it's very interesting. So v squared is equal to what? Is equal to and r is what over here? R is a divided by 2, right? So 2ga minus this, minus 2g r 1 plus cosine of our angle. Okay, so v squared, now remember that r is a divided by 2, okay? So I'm going to cut it over here. And then I'm going to have that ga 2 minus 1 plus cosine of our angle, cosine of theta, okay? Let's hope we didn't do any mistake over here. So v squared is equal to ga 2 minus 1 is 1 minus cosine of our angle, theta, okay? But v squared is equal to this part over here, so I'm going to say that ag cosine of the angle divided by 2 is equal to ga 1 minus cosine of our angle, okay? So I'm going to cut over here ga with ga, and then I'm going to have that cosine of theta is equal to 2 minus 2 cosine of theta, okay? So I'm going to have 2 plus 1, 3 cosine of theta is equal to 2, and cosine of theta is equal to 2 divided by 3. The same thing that we found in the other example, right? And it had to be, because look, notice the angle that we are taking over here for it to fall. It was the same conditions, okay? Very interesting, right? So you can put it now wherever you want. You can put it over here or here. This one is a bit better, so I'm going to put it over here. So v squared is equal to a g divided by 2 cosine of theta. Cosine of theta is 2 divided by 3. If you had memorized this, you would have done it. Like, it's weird to it's not that easy to memorize this, but at least now, when you're solving the question, you know what you're looking for, right? Like if you find that cosine of theta is equal to 10, something like this, like it doesn't make any sense, right? So now you are looking to 2 divided by 3, and you can do so over here. So we have that v is equal to the square root of ga divided by 3, okay? Let me see this. I think this is the j, okay? Your answer. So this was it. I know this video must be very long, but the discussion we made like we talked a lot about force and energy and circular motion, and we did many examples, and it was like until now, from the questions that I made from the maths, I think this was the hardest, and it's very interesting because it's from Galileo's book, right? Like, it's an example, it's a famous example, but it's hard. So I hope it helped, and solve it by yourself. So solve both examples by yourself.